Hello, my name is Brant Ross, and I am with EngineSoft USA. It's my pleasure today to discuss with you high-fidelity simulation of dynamic axisymmetric structures with process automation. So today we will discuss an example of a drivetrain component. These components tend to undergo many cycles and have high loads, dynamic loads. So in particular, we will look at a constant velocity joint and specifically the boot that protects that joint. And these boots may have large transmission angles, and so that might be very interesting from a structural point of view. And the CV joint boot is an axisymmetric structure. So we will review the steps that we went through to get very accurate results, and we will then show automated process to help make that simulation task more efficient and more approachable. CV joints have been available for quite some time. Here we see a patent application from 1928, but they became very popular as we came to have more and more front-wheel drive vehicles. CV joints are also used in off-road four-wheel drive vehicles, and in some of these applications the transmission angle may be very large. In particular, with off-road trucks, the suspensions have very high rate or amount of travel, and with the combination of the large travel and possibly having the steering be to one side or the other, that may result in a very high transmission angle. So some years ago we worked with a company called Mystiquay. They manufacture high precision parts and assemblies. One of their clients requested a half shaft that could operate with an increased transmission angle. The current CV joint boot that they had was already at the operating limit, and they wanted to be able to apply the best technology so that they could understand the limit that the current CV joint boot had, as well as technology to assess a new design. So they contacted EngineSoft USA to provide them with the solution. And this is the results of the simulation that we did those years ago. And here we see that at the very highest transmission angle, that two of the upper folds are collapsing at the outer tip, and we can see a dynamic situation occurring with the dimpling of this boot. Here's the same results, but looking at stress values. So this is von Mises stress, and we can see that in the upper folds that we get high stress at the tips, and that high stress is released when the structure collapses. But this traveling dimpling of the structure can be a problem, because as the boot turns, then that high level of deformation is traveling, and since the material is more like a plastic than a rubber in this case, that deformation will cause failure in just a few number of cycles. So the client was very happy with our results, and we actually weren't sure why until they sent the images you can see at the bottom of this slide. And in comparing those images with the simulation images, we can see that there was a high level of agreement between the two. And so how was it that we could get this high level of agreement? So we'll walk through the different steps that we took in putting together this model that gave us these accurate results, and then we will show some automation later on. So the client first had the geometry in the NX-CAD system, and so we started with that solid geometry. We could import it directly into the RecurDyn software, which is the software we use for the simulation, which could do multi-body dynamics for the large motions, as well as representing a nonlinear finite element model as part of the assembly. So in modeling the boot, these boots are blow molded, so the thickness of the boot is changing throughout from one end to the next. And in looking at the structure, we saw how thin it was. So we thought about using 3D elements, but that would have not been efficient. The runtime would have been extremely long. And since bending was such an important part of this simulation, that was another reason to use 2D topology elements, namely shells, that would have the rotational degrees of freedom and could allow us to model this boot with a fairly reasonably low number of elements. Then in trying to generate the mesh for the shells, we found that the complex boot geometry prevented us from doing automatic mid-surface generation using the NX capabilities. So we manually created the mid-surface profile, and by looking at the boot cross-section, and then we then basically revolved that profile around the axis in order to have the accurate mid-surface. So this shows the meshed mid-plane of the boot. So then an additional issue was to be able to enter in all the different boot thicknesses. So we had the information on the different thicknesses basically from a drawing, and we took all of that information and entered it into a spreadsheet. And we can see here the spreadsheet showing the profile of the boot, and then also showing the thicknesses there in the bottom chart. And we will see a chart like that a little bit later on, but you can see how the thicknesses vary abruptly along the structure. And so then with that spreadsheet, we could import the spreadsheet into the CAD software, and then we could apply that to our shell mesh of the boot. So then we had to prepare the boot ends. In this case, the boot ends did not match the geometry in the half shaft that the boot was attached to. So we actually had to expand the small end and contract the large end in order to make things match. And we did that by applying a pressure either to expand or contract those elements. We had other boundary conditions we used to constrain the motion along the direction of the axis and so forth to keep the structure stable while we were adjusting the size of the each end. So this shows the different models that we had worked with in this progression to get things sized correctly. So we started out with the first model, and we applied an inward pressure to compress the boot at the small end so that it would match with the outer diameter of the shaft. And at the same time, we applied an outward pressure on the large end because it needed to be expanded to fit over the bell housing. So that was our first model. We ran the simulation with these pressures, and so the small end contacted the shaft surface, and so then that was at the right position. And in the case of the large end, that outward pressure expanded the boot enough so that it could fit over the bell housing. So then with those pressures on, they were still on at the end of the simulation. Then after the simulation, we did what we call a model extract to save the model in that new state with the flexible body deformed according to the pressure. And that was our new model, and that was our new starting point. So then with the new model, we then modified it to lock in the small end because it was in the right position, and to then add contact with the bell housing and release the pressure on the large end. And then we ran that simulation everything was sized correctly, so then we had our third model, and then we locked in the large end so that everything would match. So then with the nodes in the proper location, the way we locked them in was to create a force distributing rigid element. Since everything was attached by contact to those rigid bodies, we weren't worrying about the boot at those locations, so we locked everything into place. So a force distributing rigid element is like a RBE element in Nastran, and it just fixes all the outer nodes to a master node in the center. And then we could use the master node to apply a constraint to attach it to the respective body, whether it was the shaft or the bell housing, and that locked in the ends of the boot properly. So the final step was to then take that model and compress the boot to be in its installed position. So you can see here the level of compression, and then finally we're in the correct configuration to actually rotate the assembly and apply the transmission angle. And the final step was to apply contacts between the upper and lower surfaces of the adjoining folds in the boot. So each combination of upper surface of one fold with the lower surface of the fold above it, each one of those was a separate contact, and the contact was defined between the element surface, all the different elements, all those different surfaces, and then also having a thickness taken into account with that contact. The input into the dynamic simulation was to bring the CV joint up to speed, and at the same time come up to a starting transmission angle. And then as we proceed through the simulation, as we increased the transmission angle, we decreased the speed according to the client's specifications, because the higher transmission angles corresponded to higher steering. And when you have the maximum steering applied, the vehicle is not going to be traveling at the fastest speed. And so this takes all that into account. So again, we end up with the result that we showed earlier with this dimpling with the large transmission angles. And the reason we got the correct results is because we put this structure, we pre-stressed it into its assembled state so that it was ready to then provide accurate answers. And again, if we take a look at the stresses, we can understand where the high stresses were and understand why the dimpling occurred on the outer edges, the outer tips of the folds at the top there. So now we're going to look at some automation that's been done more recently. This is a little bit different boot, but we will see how this process is done. So we start out with the boot geometry. We do a Boolean operation to cut it in half so that we have access to the profile curves. And as we look at zooming in on this portion here, we'll go through the first step, which is to identify the two profile curves. So we pick the outer curve, inner curve. You can see a custom dialog box. It allows us to just select the curves. So the process is very quick to do. And now you can see a mechanism has been created, and these different objects here are following along the profile curves and generating the mid-plane curve. We've tried this out with I think 8 different boots, and it works robustly with all of them. You can see that chart of the thickness of the boot looking just like what we had obtained earlier from the drawing in the earlier project, but now it's created automatically from the geometry. So this shows a zoomed in view of what's happening with our little mechanism that we're using to create the mid-plane profile. And you can see at some of the really sharp corners, things will back up a little bit. The middle ball will back up a little bit. but we filter through all that so that we can get the mid-plane profile without any of those anomalies. And so then with that, we can go through the next stage of the process, which is to just go ahead and create a mesh. And you can see all the details in the mesh. The user can control the resolution of the elements at the outer tips as well as at the root of each fold, because that's the most sensitive thing to get accurate results. And here we're seeing with the thickness of the element applied graphically. So that's a preview mode. Now with that boot, we're ready to apply it with the half shaft assembly. So we have a model with the half shaft. On that model, we are laying out some location, and now we're indicating other information to just basically import the file that has the boot in it. So that's now merged in with this model. And then we have the ability to select locations on the half shaft and use that to align the boot. And it will tell us, information about the size of the boot versus the location points on the shaft and the bell housing. And then we can go ahead and apply the proper situation so that we can compress the boot along its axis in order to get it into the correct configuration. In this case, we aren't doing the resizing of the two ends because the client we're working for on the automation, their assemblies didn't have that issue. So we haven't addressed it with the automation, but that could be added in later on if somebody else had the need. So we can see that the model is all assembled. The remaining step here is to define some of the contact information. So we can pick rows of elements as well as geometry on the bell housing here. And you can see we just pick one element for each series of elements around the circumference. And so we just pick all the different rows that might make contact, and that's what's going to be included in the particular contact. So we do that at each end. The contact between the folds has already been done automatically. So at this point we're just calling out the shaft geometry that the bottoms of the folds could possibly interact with. And now we're able to run our simulation as before with high fidelity, all these contacts, nonlinear flex body behavior, but the model definition now is much more efficient than it was before. So with that, let's move on to the next slide. So in summary, it's now possible today to accurately model these nonlinear flex bodies that are interacting with rigid bodies in an assembly, and we can simulate them, include contacts, and so it's now possible to do this. Second point is that to get accurate behavior, we need to be able to replicate the assembly process so that our flexible body is in its proper pre-stressed condition. And finally, by using process automation, the simulation is now much more efficient, more approachable. For engineers who might want to do this, you don't have to be quite as a specialized analyst to be able to do these sophisticated things with the process automation. And so that's democratization to allow for a wider range of users, and also because the time to learn all the techniques is much reduced because the automation is also guiding the engineer through the proper process. So thanks very much for your attention, and I'm glad I could present this to you. Please contact me if you have any questions. Here is my email address, and I'll be glad to respond to any questions you may have. Thank you.